Hi everyone, welcome back. In this video and the next video, we are going to look at how potential energy changes in a gravitational field. Okay, so here's our dot point from the study design. Analyze the use of gravitational fields to accelerate mass, including potential energy changes in a uniform gravitational field. The key word here being uniform. Right, and we're going to be using the formula that you're familiar with. Okay, the change in gravitational potential energy is equal to mg times the change in height. Fair enough. All right, so that's pretty straightforward. We've done that before. Let's take a look at what we're doing. Okay, so just a little bit of a reminder. Work is defined as a change in energy of some kind. Okay, in order to change the energy of an object, you need to do work on it. Okay, what we're going to be talking about is the case where gravity is doing the work on an object, which means it is probably going to be pulling it down towards the ground, in which case its gravitational potential energy and also its kinetic energy is going to be changing. Okay. There is another definition for work, which is, whoa, what happened there? Which is work is equal to the force multiplied by some distance. Okay, so if you apply a force to an object over a certain distance, then you can calculate its work that way. Okay, so long as the force applied is in the same direction as its motion. Otherwise, you have to introduce a cos theta symbol in there. So when we're talking about work in terms of how gravity does work on things, okay, well, what's the force due to gravity? Well, we know that it's mg, whatever g happens to be, multiplied by the distance that the object travels. And if the object is traveling vertically, because that's the direction that the force is being applied, then the distance traveled is delta h. Okay, and that's where basically that formula comes from. Okay, so just think about it. I mean, if you are up in the sky and you drop an object, the object is going to start falling down because that's the direction that gravity is exerting the force on the object. And its potential energy would be decreasing because we're taking the ground to be zero, so its height is becoming less and less. And according to this formula, then its gravitational potential energy is becoming less and less. However, its kinetic energy is also increasing. Okay, so usually a decrease in potential energy generally means an increase in kinetic energy and vice versa. All right. Now, we're talking about uniform gravitational fields. Okay, so this formula only applies when your gravitational field is the same strength everywhere and also the same direction, but mainly the same strength. So we're going to be looking, at least in this video, for distances which have, I should have worded this differently. We're looking at distances that change by no more than, say, 10 kilometers. Okay, so consider an object 10 kilometers up in the sky and it falls down towards the ground. Okay, we can consider that 10 kilometer region to be uniform gravitational field, where the value of little g can be taken as a constant. Okay, it can be taken as around equal to 9.8. And that's fine. Okay, we can use this formula because g is constant. But once you start going outside the realm of a 10 kilometer change in distance, then the value of little g is going to change. Okay, just think about it. The further out you go from Earth, the smaller little g is going to get. So for objects falling in from, thousands and millions of kilometers away, you have to take into account the fact that this value here is not going to be constant anymore. Okay, so we need some other way to work it out. However, if that value is constant for a relatively small change in distance or a relatively low altitude, then we can just go ahead and apply the formula. Okay, so let's do a question. A 70 kilogram skydiver jumps from a plane at an altitude of 9 kilometers. What is the change in energy once they reach an altitude of 5 kilometers? And how fast are they traveling at this time? ignoring air resistance and terminal velocity. Okay, so we've got this skydiver jumping out of a plane. Here's a plane, skydiver jumps out, whee! All right. So the height from the ground is 9 kilometers. However, we're now talking about what their energy, or rather the change in energy, has been once they reach a height of 5 kilometers. Okay, so looking at this jumper, what is their change in height? What is their change in distance? Well, that's just 9 minus 5, which is 4. Okay, so we can just go ahead and apply the change in energy formula. Okay, change in gravitational potential energy is just equal to mg delta h. We're allowed to use this because their change in height is, much smaller than, say, 10 kilometers. All right, so g can be taken as a constant. So we can multiply all those things together. 70 times 9.8 times 4. And let me just type it in my calculator. It's 4,000. So we're to talk about meters. So it'd be 2744000 joules. All right. Cool. So that's their change in gravitational potential energy. Now the second part of the question says, how fast are they traveling at this time? This is almost like a Unit 3 question. Area of Study 3 question. Okay, we're talking about changes in energy. So you're losing gravitational potential energy, but in doing so, you're gaining kinetic energy. So this value here is actually equal to your kinetic energy. All right, so we can go ahead and say that my kinetic energy is equal to half mv squared, which is equal to 2744000. All right, and our job here is basically to calculate V, which we can see is going to be equal to 2 times the mass of this, 2 times this energy here, so 2 times 2744000 divided by the mass of the skydiver, 70, and you end up getting something along the lines of 280. Okay, it might be slightly different because I worked it out slightly differently before. So let me just double check that. You should be double checking all these calculations as well, just in case something's gone wrong somewhere. No, I get 280. Cool. So 280 meters per second. Now that seems super fast, but you got to remember we're ignoring air resistance and terminal velocity, so we're in perfect physics land for this question. Okay, so there you go. We can calculate a final velocity if we know what the change in gravitational potential energy is. Pretty straightforward. We just equate the loss of gravitational potential energy with a gain in kinetic energy, and then just use the kinetic energy formula to work out velocity. Cool. All right, next question. How much work is needed to be done to lift a hot air balloon of mass 1,000 kilograms, 3.2 kilometers? Okay, so we have to change the height of this hot air balloon. So we have to do some work on it. We have to change its gravitational potential energy. We're going to start increasing it. So we're going to put work into the system to increase its gravitational potential energy. So how do we work that out? Well, we go back to our definition of work, which is that it is a change in energy. What change in energy are we talking about here? We're talking about an increase in gravitational potential energy. So we're going to do mg delta h and just multiply everything together. Okay, and again, because our change in height is much less than 10 kilometers, then we are allowed to assume that the value of little g is going to be constant. So it'll be 1,000 times 9.8 times 3,200 meters. And that's equal to around 3.14 times 10 to the 7 joules. Okay, so quite a bit of energy needs to go into changing the height of this hot air balloon. Okay, so that's pretty straightforward. Okay, working with uniform gravitational fields where the field strength is assumed to be a constant, pretty easy. Okay, you just use your mgh formula that you're used to using, right? And you can turn it into kinetic energy and then work out velocity from that if you need to. All right. Okay, so yeah, like I just said, in the last two questions, we assumed that g is constant, okay, because you're not changing your height that much. So the value of g isn't going to vary that much. You can just assume it to be the same number. However, if we're talking about objects like this asteroid here in this picture, or say satellites moving between, orbits, then the value of g is not going to be constant. Okay, the value of g for this asteroid here is going to be much, much smaller than the value for g once it's at this position, okay, because it's just moved so much closer to the Earth. All right, so if you're trying to work out what its change in energy is from this point to this point, you can't just use mgh, because the value of g itself is changing. All right, you need some other kind of method to work it out. You can't just use the formula, because the formula assumes that the g is just one number and one number only. However, we can't, because g is different here, it's different here, it's different here, it's different at all these places. Okay, so you can't just use that formula straight away. You can't even use this force here, this equation here, because the force is not constant. The force of gravity on the object here is much less than the force of gravity on the object here. Why? Well, because force is equal to mass times little g. So if little g is not constant, then the force is not going to be constant. All right, so you need some other method to work it out. So there we go. That's it for this video. Okay, we've looked at a uniform gravitational field, and we've looked at how its potential energy changes using this formula here, assuming the g is constant, because you're not changing your height that much. Okay, so when you're changing your height on the order of, thousands of meters, then you can just assume little g to be constant. However, outside of this range, you cannot use this formula, because little g is not going to be constant. Okay, and in the next video, we're going to see what we can do in that situation. All right, so that's it for this video. I'll see you in the next time.